So in this video, we will talk about Newton's second law of motion. But given that the second law features the concept of mass, let's first talk about what mass is. Here, it says that mass is a property that specifies how much resistance an object exhibits to changes in its velocity. So the more mass an object has, the more resistance it has to its change in velocity. So if it is currently not moving, it will take a whole lot more force to get it to change its state of not moving if it were a much heavier mass. Imagine playing catch with basketball or a bowling ball. Which ball will be more likely to keep moving when you try to catch it? Which ball requires more effort to throw it? Well, the answer, of course, is the bowling ball. And that is because the bowling ball has more mass. So it takes more force to throw it and more force to stop it if you are trying to catch it compared to the basketball. In the physics language, you say that the bowling ball is more resistant to changes in velocity than the basketball. So how do we quantify this concept of having more resistance? Our quantification of that concept is by the property called mass, whose SI unit is kilograms. So mass, again, it's the property that specifies how much resistance an object exhibits to changes in its velocity. Experiments have shown that the greater the mass of an object, the less that object accelerates under actions of given applied force. For example, you have an experiment that compared the acceleration given by a force that a force produces on different objects. So when you have a force that acts on an object of mass 1, it produces an acceleration A1 on that object. And then you apply the same force on another object of mass 2, and that produces an acceleration of A2 on that second object. If you do a ratio of the two masses, mass 1 and mass 2, you find that there is an inverse ratio of the magnitude of the accelerations. For example, if a force acts on a 3-kilogram object and an acceleration of 4 meters per second is produced, 4 meters per second squared. If you apply the same force to a 6-kilogram object, the acceleration produced is half of 4, which is 2. So the magnitude of acceleration of the object is inversely proportional to its mass when acted on by a given force. If one object has a known mass, the mass of the other object can be obtained from the acceleration measurements. Mass is an inherent property of an object, and it is independent of the object. The weight of an object, the weight is actually the magnitude of the gravitational force exerted on the object, and it varies in location. For example, if the weight of a person is like 360 newtons on Earth, its weight on the moon is 1/8 of that, or if I'm not mistaken, 40 or 40 plus newtons. But the mass of the object is same everywhere. If an object has a mass of 2 kilograms on Earth, it will also have a mass of 2 kilograms on the moon. So now we are ready to talk about Newton's second law. Newton's first law explains what happens to objects when no forces act on it. Again, no, when no forces act on an object, it will maintain its original motion. Either it will remain at rest or move in a straight line with constant speed, as observed from an inertial reference frame. So Newton's second law answers the question, what happens when more forces are acting on an object? Imagine pushing a block of mass m across a frictionless horizontal surface. The horizontal force on the block causes the block to move with an acceleration a. If you apply a force twice as great on the same block, the acceleration of the block doubles. So what does this tell us? This tells us that the acceleration of objects are directly proportional to the force acting on it and inversely proportional to the mass. So acceleration is directly proportional to the force and acceleration is inversely proportional to the mass. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This is Newton's second law. The net force here actually is the resultant. If you remember the resultant vector, it is the sum of vectors. So in this case, the vectors you are dealing with are forces. The net force is the resultant of force vectors acting on single object. So, with a proportionality constant of 1, the Newton's second law equation is net force is equal to mass times acceleration. The acceleration, this equation is all about the acceleration due to the net force acting on an object. So on the left-hand side of the equation, that is called the net force. Other words for net force are total force, resultant force, unbalanced force. But they all mean the vector sum of all the forces acting on an object. So an important skill that you need to know is to determine what are the forces acting on the object, both the magnitude of the forces and the direction of the forces acting on an object. And you also need to know how to add them using component method or parallelogram method or polygon method, those methods that we learn about. There are many forces that may be acting on an object, but there is only one acceleration of the object. For this particular equation, we also have component equations. So, right, this is, if you remember our motion in 2 dimensions, we can extend that here. In fact, this is an example of motion in 3 dimensions. We can look at only the x components of the force and correspondingly the x component of acceleration, the y components of the force, the y components of acceleration, and even the z components of the force and acceleration. Let's answer this question. An object experiences no acceleration. Which of the following cannot be true? Cannot be true for the object. Letter A, a single force acts on an object. B, no forces act on the object. C, forces act on the object, but the forces cancel. So what is your answer? The answer is A. If a single force acts on an object, this force constitutes the net force, and there is an acceleration according to Newton's second law. So if there's only one force acting on an object, that object will not be canceled by another force because there's no other force. So therefore, that single force becomes the net force, which causes acceleration for the object. So you push an object initially at rest across a frictionless floor with a constant force for a time interval delta t, resulting in a final speed of v for the object. You then repeat the experiment, but with a force that is twice as large. What time interval is now required to reach the same final speed? The answer is delta t over 2. Why is that? With twice the force, the object will experience twice the acceleration. Because the force is constant, the acceleration is constant, and the speed of the object starting from rest is given by, if you remember, if the object starts from rest, v final equals v initial plus acceleration times time. So the final velocity is directly proportional to the acceleration. With twice the acceleration, the object will arrive at speed v at half the time. These are the SI units of force, the Newton. Force of 1 Newton is a force that, when acting on object of mass 1 kilogram, produces acceleration of 1 meter per second squared. For the US customary system, the unit of force is the pound. The force of 1 pound is a force that, when acting on a 1 slug mass, produces acceleration of 1 feet per second squared. Here's one convenient approximation. 1 Newton is roughly around a fourth of a pound. Why do you move your hands backward when you catch an egg? Imagine holding your hands stiffly and not moving them as you catch the egg. Egg will hit your hand and be brought to rest in a very short time interval. That means that the magnitude of the acceleration of the egg will be large, right? Because the change in velocity of the egg will be so abrupt, from moving very quickly to stopping at such a very short amount of time. This requires a large force from your hands because large acceleration is caused by large force. And this large force is sufficient to break the egg. But if you move your hands backward and slowly bring the egg to rest, what you're doing is actually reducing the magnitude of the acceleration or change in velocity of the egg. So this means that you are essentially, with a smaller acceleration, you are applying a small net force and the egg does not break. When you throw an egg into a sheet, SHEET, something similar happens. When the egg strikes the sheet moves in same direction in response, bringing the egg to a lower velocity over a relatively long distance. Here's an example. A hockey puck having a mass of 0.3 kilograms slides on the frictionless horizontal surface of an ice rink. Two hockey sticks strike the puck simultaneously, exerting the forces on the puck shown in the figure. The force F1 has a magnitude of 5 newtons and is directed 20 degrees below the x-axis. The force F2 has a magnitude of 8 newtons and its direction is 60 degrees above the x-axis. Determine both the magnitude and direction of the puck's acceleration. Now, using what you know from vector addition, all you really need to do is add these two vectors. You get the x components, y components, you combine all the x components, combine all the y components, and then you use the Pythagorean theorem to get the magnitude of the net force, or the sum of these two forces, and then the direction as well of those. And then when you finally have the net force, you get the acceleration by using the formula acceleration is equal to net force over mass. So basically, that's what we will do, no? So the net force along the x is equal to the F1x, which is the x component of F1, and F2x, which is the x component of F2. And here, we have all of these, F1 cosine theta and F2 cosine phi, or phi. So the net force along the y is just the y component of F1 plus the y component of F2. And so the acceleration along the x is the sum of all forces along the x, the net force along x, divided by m, which is the mass of the hockey puck. And acceleration along y is the sum of all forces along y, or the y components of the force divided by mass. So when we substitute values, we find that the acceleration has an x component of 29 meters per second squared and a y component of 17 meters per second squared. And if you use Pythagorean theorem to get the magnitude of that acceleration, you get 34 meters per second squared. And if you use tangent theta, the formula to get the angle, you will find that the answer is 31 degrees above the x-axis. So that would be all for our lesson on second law, and we will learn more about this topic during our face-to-face classes. Goodbye.